Hi everybody, welcome to lecture number 2, which is actually 1A because this is taking a bit of a detour into psychophysical methods and TSD. Here are the learning outcomes. I'll talk about some classical psychophysical methods. They're called classical because they were the first to be developed, and they were all about measuring absolute thresholds, and I'll explain what that is. Next, I'll talk about JND, what that stands for, and how that can be measured. And as we go through this, things are getting progressively more complex. So we are starting off with kind of simpler things and building upon that. With number 3, pretty complex. I'm asking about the differences and I guess the similarities too between Weber's law, Fechner's law, and Stevens' power law. I'll go into a bit more detail on Stevens' power law, discussing the evidence that supports it. And then I'm going to talk about the main problem with everything I've talked about up to this point. So the main problem with classical psychophysics. From there, I will switch gears a little bit and explain the theory of signal detection, or TSD. Some of these are not going to make any sense whatsoever now, but hopefully after I've discussed them, things will fall into place. I'll talk about the ROC curve, the response criterion beta, and sensitivity D prime. And finally, I'll talk about the effects of subliminal stimuli. But first, classical psychophysics. Quick definition of psychophysics. It is an unusual word because it is where psychology meets physics. We can describe the physical world around us and quantify it using physics, but then we also want to talk about our experience of the physical world. Now, if our experience of the world around us was isomorphic, that is, if it was a one-to-one correspondence with the physical quantities, we wouldn't need a field of psychophysics. But as we'll see, there is not always a one-to-one correspondence, so we do need to do a bit of investigation into the relationship between the physical quantities and what goes on inside our heads. Now, the very earliest psychologists were interested in perception, as I mentioned in the previous lecture. I think they wanted to start off with something simple, something that they could kind of wrap their arms around and get that over with before moving on to more complex things like the mind-body problem. Okay, study perception. Where are we going to start? I guess you could start with vision. I guess you could go that way. But then even within vision, where do you start? I suppose you could start by measuring the limits of our senses, starting with the faintest, dimmest, smallest stimuli that people can still actually perceive. Now, the term for this is the absolute threshold. So it's something that is just barely reaching into your conscious awareness. The archaic term for this is a Lyman, which isn't used anymore, except as part of the word subliminal, which I'll come back to at the very end. I have an older definition for absolute threshold. I've lost my reference for this, but it's the point at which physical stimulation enters into consciousness, and that is a very 19th century kind of definition. And this is based on an idea called threshold theory, that you might have a physical stimulus, but it's too small, there's not enough of it, for it to enter into your consciousness. So maybe objectively, it's there. You can measure it with equipment, but you can't tell that it's there, at least not with the naked eye. And threshold theory says that there is a very sharp inflection point where things suddenly enter into your conscious awareness. So let's take a look at the prediction made by threshold theory. That is the red line, or the square step function here. So what we have along the x-axis is stimulus intensity, and then on the y-axis, well, this is kind of the dependent variable that corresponds to the x-axis independent variable. The y-axis is the percent of times that the person says yes when the stimulus is presented. So again, the prediction is made by threshold theory. It says that, at this case, at 6 units of stimulus intensity, the person goes from never saying yes to now suddenly saying yes 100% of the time. That's what the theory predicts. But if you actually go and collect data, show people stimuli that vary in intensity, and measure the percentage of times that they say yes, they see it, you don't get the nice step function. What you get actually is this S-shaped sigmoid function. Oh, well, that's really not what we expected. Now, when the data don't match your theory, as a good scientist, what you need to do is go back to your theory because the theory is wrong. The data have to be correct. If you get the same data over and over and over and over and over again, you need to work on your theory. And that's not what happened. No, I mean, they were so in love with threshold theory, they decided to make the data fit the theory. Oh, that's kind of weird. So what they decided to do was take the point where the person says yes, they're detecting it 50% of the time, trace over to the sigmoid function and then go down, and then by definition, the threshold, the absolute threshold, would be 6 units of stimulus intensity. So the classical psychophysical definition for the absolute threshold is actually based on a relative criterion. Oh yes, greetings, bitter irony. Yeah. They were okay with it at the time, but it's kind of embarrassing to look back on it now. Oh well, we're kind of stuck with that now. But I haven't told you, how do you get that sigmoid function in the first place? Okay, let's take a look at the actual measurements that are a part of classical psychophysics. There are 3 very common ones. The first one is called the method of constant stimuli, and it's not what you think it means. Oh dear. Yeah, so the word constant, in this case, means predetermined. That is an archaic sense of the word constant. If you hear the word constant, you probably think unchanging. And that is, ironically, the exact opposite of what's happening in the method of constant stimuli. Isn't it good that I'm here to guide you through all of this confusingness? Okay, so with the method of constant stimuli, what you do is get some random numbers, which of course you would look up in a book. Yes, you would look them up in a book. And what you do is you'd calibrate your equipment within a particular range. So I'm going to pick 0 to 100 lumens, which is a physics unit of the intensity of light. And then within that range, randomly pick out some values. And yeah, you can repeat values. That's completely fine. 8 is in there twice. So take your equipment, carefully calibrate it to produce 8 lumens, and then get an observer. That is the term that's used, not a subject or a participant, but in perception, we use the term observer. Who is this observer? Are they a highly trained, skilled, intelligent person? Not necessarily. Just someone off the street? Or, well, somewhere in between. There was a fundamental distrust of observers, so they wanted to make things as simple as possible. What could be simpler than saying yes or no? Yeah, it doesn't get much simpler than that. So the task for the observer was to be in a completely dark room, squinting to see these lights, and all they had to do was say yes when they thought they saw a light. Okay, simple as possible. Each observation is a trial, and there are many trials. In grad school, I signed up to do some experiments, and I was in a very dark room, squinting at a dim computer display for thousands and thousands and thousands of trials. Okay, you record the observations, you get a bunch of numbers, and nobody wants to look at numbers, so hey, how about a picture? And when it comes to science, a picture means a graph. So here is the graph. So once again, we have our x-axis, which is the units in terms of physics, the independent variable. Y-axis is the dependent variable, a person's inner subjective experience. So this is very much a psychophysical graph. Y-axis for psycho, x-axis for physical, psychophysical, putting the two together. You get the S-shaped function. You start at the, in this case, proportion, 0.5 of yes responses, trace over, map down, and there you get your threshold. Now, they didn't pick 0.5 randomly. 0.5, or 50%, means that your chance of saying yes and no are equal. like even if you're just sort of guessing. Every method has its strengths and weaknesses. Here are the pros and the cons for this one. It's actually pretty accurate. It gives you a pretty good estimate of a person's threshold. The downside is, even if you're really fast at calibrating your equipment, it is pretty time-consuming. And that's assuming that you know the proper range. Look at your absolute threshold isn't between 0 and 100 lumens. It's more like between 0 and 10. Actually, it's more like between 0 and 1. So you kind of got to know where to start off with in the first place. We're also going to be asking more things of our methods, like, hey, does your threshold change over time in a phenomenon called dark adaptation? You're in the lobby of a movie theater, it's pretty light and bright, you go into the theater and the previews have started, it's kind of dark. You can't really see anything until your eyes adjust or adapt. It takes about 20 minutes. So your threshold, your sensitivity, must have changed over time. How do you measure that? Well, you cannot use this method. It simply doesn't work for that. That's okay. We do have some other methods. The next one is called the method of limits. The method of limits uses monotonic change. That's just a fancy word that means change in one direction. Things can either go up or go down. Going up means an ascending series. You start with values that are pretty much below the person's absolute threshold, and you gradually increase them monotonically until the person says, yes, I see something now. Or you do the opposite. Start with something that is very obviously perceivable and decrease the intensity until the person says, wait, no, stop, I don't see it anymore. And this one can be used to track changes over time, but you know what? It actually introduces two new errors. One is errors of habituation. So if you're doing something dumb, like you've got this huge range of 0 to 100, you're starting off with 100 and you're going down, 99, 98, 97, it's going to take a long time before there is a change, before the person cannot see the light. So they're going to be sitting there going, yes, I see it. Yep, still see it. Yes, yes, yes. What's going to happen is that the person will kind of disengage from the task, and they're not really paying attention, and now there is a change, and then they've missed it. They have habituated to something that is really not changing. So that can be a problem if you've got the range too large. It can also induce another kind of error in which you're maybe really close to the threshold, and you say, yes, I see the light. Yes, I see the light. Yes, I see the light. No, I don't. Okay, repeat it. Let's try this again. Yes, 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 no. Oh, I get it. Try it again. Yes, 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 no. There's a pattern. Let's try this again. Okay, I'm going to say 3 yeses and then a no. How about a triple yes and then a no? How about 3 mm-hms and then 1 mm-mm? So again, the person has disengaged from the task. They're counting their responses more than they're actually observing, and those are called errors of anticipation. So those are potential problems as well. Now there is a subtype of the method of limits that can overcome some of these new errors. Generally, it's called adaptive testing, and this definition is really not great because there are so many different kinds of adaptive testing. I'm going to go with one that's the most straightforward. It's called the staircase method. So it does use the ascending and descending series, and you switch back and forth between the two. And when you switch over, you don't start it at the same point and then like go downwards again, but you change the starting point so the person can't count anymore. Now what you might find is that the threshold varies on each trial. We're not going to worry about that. The answer is just take the mean. I know this is kind of vague, so let me show you like a visual example of the staircase. So this just shows 3 trials. Each row represents a different trial, and these are the stimulus values. Trial 1, the right arrow means it's ascending, so we're starting at 97, and the threshold we're guessing is around 100 units of whatever it is. So the person says no, 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 and then at 102 they say yes. Now you might think, okay, the threshold there's 102, but technically something changed between 101 and 102. So we split the difference and say it's 101.5. Trial 2 is now a descending series, and we're going to randomly start at 104. The person says, yes, I can see it. Yes, 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 no. Again, we're going to say the change is somewhere between 99 and 100, so 99.5. Trial 3, another ascending series, and look at, now we're starting at 98. We're not telling the observer this. They don't know this. They can't tell. They'll say no, 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 and then yes. So again, splitting the difference 100.5. We've gotten 3 different values for the threshold. Where is it at? We'll just take the mean, and in this case it works out to be 100.5. Now you wouldn't just do 3 trials, not 30, not 300. If you want to get some really good data, you go up to 3,000 trials. You know what? You're participating in this. You're going to be here for a while. There's one last method, and I'm saving the kind of most obvious till the end, called the method of adjustment, in which the person actually gets to touch the equipment. Now this would otherwise not be allowed. You want someone coming into your lab and touching your very expensive equipment? No, don't touch it. Filthy, dirty fingers. Okay, well, in this case, you actually do let the person touch it. There might be a knob that they turn, and you'll tell them, okay, we want you to turn the knob until you just barely see the light. Or vice versa. You can see this light. We want you to turn the knob until you can just barely, and then not see it anymore. This method is quick and dirty. It is quick. It is dirty. It's really hard to get people to let go of the knob. They'll turn it up and they'll go, oh, I went too far. I gotta go back. I gotta go forward and go back, forward. It's like, no. Just like turn it up and then just let go. And people just can't do that. So it is quick and dirty. So using these 3 classical psychophysical methods, we can use them to measure the absolute threshold. And if you wonder about those, this is a very famous summary of absolute thresholds from Frank Geldard in 1953. Your vision, if you are typical, means that you can just barely detect the light of a single candle from a distance of 50 kilometers on a clear, dark night. Audition, you should be just barely able to hear the ticking of a wind-up watch under quiet conditions at a distance of 6 meters. You should be able to taste 1 gram of salt dissolved in 500 liters of water, or at least the concentration equivalent of that. For smell, you can detect 1 drop of perfume diffused in the equivalent volume of a 6-room apartment. And for touch, you can feel the wing of a bee falling on your cheek from a height of 1 centimeter. I don't know if any bees were harmed in doing this research. Now, after this has all been measured, the job is done, right? You can look up absolute thresholds in books, and it'll give it to you in even more kind of accurate quantitative terms than we see on this slide. So then what do you do? Well, that's just the simplest case of detecting the presence or absence of a stimulus. The next, more complex case is to present 2 stimuli and ask people if they can detect a difference between 2 stimuli. The term for this is called the difference threshold. So it's the smallest difference that people can detect between 2 stimuli. Yes, 50% of the time, so still sticking with that. It's kind of entrenched at this point. This does mean the experiment is a bit more complex. You're presenting 2 stimuli, and you have to keep track of those. One is called the standard, the other is called a comparison. Now the standard does not change, it's the comparison that changes. So obviously when the comparison changes, it changes the size of the difference between it and the standard. Asterisk, both of these have to be above the person's absolute threshold. They have to be able to detect both of these in the first place. The difference threshold is not usually called the difference threshold. In the biz, it's referred to as the just noticeable difference, or JND. Yes, that is seriously the name for it. Now, doing the experiment is a bit more complex, a bit more involved than the simple absolute threshold. So for example, in the classic example, you might be given a 100-gram standard weight and then a bunch of other weights maybe in your other hand, and you're asked, again, the simplest possible question, is the comparison heavier, yes or no? So again, it's still a yes or no question. Here's the graph. Oh, whoa, there's a lot of stuff going on. A lot more stuff than you might expect. And we actually don't get the difference threshold in the way that you might intuitively expect after having seen the absolute threshold. Now, we don't just go to the 0.5 point and then trace over and map down, because you get a number of about 100, roughly speaking. Now, that doesn't make a lot of sense. Can you tell the difference between a 100-gram and a 100-gram weight 50% of the time? Wait, no, it's a difference of 100 grams. So the difference between 100 and 0, 50% of the time? Or 100 and 200? See, it just doesn't work. It doesn't work that way. What you actually have to do is go to the 75% or 0.75 proportion, go over to the curve, map down. Here we get 102. That's called the upper difference threshold. Then you go to the 0.25 or 25% point, over to the curve, down. Here we get 96. And now, there's a bit of math. We have to do a bit of math. The upper difference threshold minus the lower. So that's, I got to do this in my head. Oh, no. 102 minus 96 divided by 2. It's 3. Okay, so in this case, the difference threshold is 3 grams. That means you can tell the difference between a 100-gram weight and a 103-gram weight about 50% of the time. So again, we don't go to the 0.5 and trace over and map down. But there is still this, some letters there. Okay, it's the point of subjective equality. For this person doing this experiment based on their graph, they are telling us that the one stimulus that is the most similar to a 100-gram weight is, well, whatever this number is. And just kind of eyeballing this graph, I'm going to say this is probably like 99 grams. For this person, the one stimulus that is the most similar to a 100-gram weight is a 99-gram weight. Wait, that doesn't make sense. I can do the math. That's a difference of 1. It doesn't make sense. That's perception. Okay, sorry. What these people are actually telling us is that 99 grams is indistinguishable from 100 grams. Now, the difficulty with measuring the difference threshold is, well, what do you pick for your standard stimulus? 100 grams? Okay, you got to do all this weighing and plotting and math to get the answer of what the difference threshold is. But what if you started at 112 grams? You'd have to go through the whole experiment and do all of this, and for whatever standard stimulus you pick, you're going to have to go and do all of this work. Okay, well, you know what? Who wants to do all that work? Maybe there's a way we can take a shortcut. Maybe there's a pattern in the data that means that we don't have to do a lot of work. All we have to do is a little bit of math. See, maybe math can be our friend. So this basic question was the one asked by Ernst Weber. Is the difference threshold like one quantity, or does it vary? And if it varies, does it vary in a predictable fashion? Can we describe how it varies mathematically? And he found something that, okay, well, it's called Weber's law, after Ernst Weber. Of course, that makes sense, right? And here it is, pretty simple. So K is a constant, known as the Weber constant or the Weber fraction. Is everything named after Weber? You know what? I would say if you discover a new phenomenon, the first thing you should do is name it after yourself. I call that Lopelman's law. The other things we've seen before, J and D, we've seen that S is the standard stimulus intensity. Okay, so we've got things that we've seen before. So let's just take a look at some numbers. If we do all of the lifting with a 100-gram standard stimulus, we find that the JND is 2 grams. That means it's a difference of 2%. Yes, I know the graph had it at 3%, but, things may vary. It depends on the observer sometimes. Okay, let's do this experiment all over again, starting with a 1,000 gram weight. The JND, oh, you know what? If it was 2 grams, that would be great. It would be the same. It would not vary at all, but it's a completely different number. It's 20 grams. Oh, man, wait a minute. Expressed as a percentage, it's the same. Wow, it is constant. Yeah, so for lifting weights, the Weber fraction is 2 out of 100, or actually 0.02. Now, the good news is, you can just look this stuff up in books. It's been published back in, 1971 for all kinds of things. Light intensity, sound intensity, even for different frequencies of vibration presented to the fingertip. So it gets pretty darn specific. Now, the advantage of this is, if you start with whatever random standard stimulus, like 112 grams, oh dear, what is my difference threshold? You don't have to do the experiment. You just plug some numbers into the formula, and it will tell you what the JND is. Beautiful. Except the law, Weber's law, I'm saying that, putting it in quotes, is not a law. A law is valid under all conditions. Weber's law is not. So it breaks down as you get close to absolute threshold. So let's see. Let's pick a standard stimulus that's pretty low. I'm going to pick one of 0.000000001 grams. Okay. Now what's the JND for that? I don't know, because a weight of 0.000000001 grams is probably less than the weight of a period on a piece of paper. It's below our absolute threshold. It doesn't make sense. Okay, yes, it's a ridiculous example, sorry. As you get closer to the absolute threshold, the values you get from the formula diverge from the actual data if you had been lifting the weights. So that's a problem. It's not really a law. It also breaks down at the upper end. So what if you have a weight of 100 million grams? Hold that in one hand. How much of a weight do you have to hold in the other hand to detect the difference 50% of the... What? How many million grams? That's like the weight of a Volkswagen. You can't even lift that. So, yeah, sorry. It's another ridiculous example. But the point is, as you get to greater quantities, what you get from the formula does not match the actual data that you get. So at best, Weber's law is not a law. It's an approximation. But people kind of didn't realize that right away. Ooh, that's too bad. Instead, what people did was move on to the next problem. Okay, so we've been through detection of a single stimulus, the absolute threshold. Comparing two stimuli together, measuring the difference threshold, or JND. What do you do after that? Well, the next challenge is called scaling. So far, we've just been asking people yes or no questions. Can you tell a difference, yes or no? So you can tell the difference between a 100 gram and a 103 gram weight, okay, about 50% of the time. But what about 100 versus a 200 gram weight? Okay, there is a difference, and you can tell there's a difference, but the size of the difference is different. And this is called scaling. And this is trying to answer the question, how big is the stimulus? How big does it seem to you? So here's an experiment you can try for yourself. Now wait till it's completely dark, and then go into a room that has two identical lamps. If you turn on one lamp, one light bulb, okay, yes, it's noticeably brighter compared to complete darkness. But then turn on the other lamp. Okay, yes, you can tell that you've turned on a second light source, but ask yourself this. Does it seem twice as bright than having just one light bulb? And the answer is going to be no. This is a case where our experience does not match the underlying physics. You've just doubled the light energy in the room, but it doesn't seem twice as bright. So this is the reason why we need psychophysics. There isn't an isomorphic or one-to-one relationship. If you turn on 2 light bulbs and it seems twice as bright as one, okay, it's isomorphic. We wouldn't need this branch of science. But it's not twice as bright, so now we need to answer the question, well, how much bright does it seem? Now, there are 2 ways of answering this question about scaling. I'm going to go with the less obvious one first because I'm going chronologically. It's called indirect scaling. And it's a way of getting numbers, magnitude, from difference judgments. Difference judgments are all about, can you tell the difference between this, yes or no? So it's a very clever kind of way of getting numbers based on asking people yes or no questions. And this was the great insight that Gustav Fechner had. Fechner, we believe, was a student of Weber's, and he derived a scale for magnitude that was based on Weber's law. So that's one basic assumption. Weber's law is valid. Oh, do you remember what I talked about in the previous slide? It's not valid. It's not a law. It's an approximation. Ooh, too bad, Gustav Fechner, but let's see what he makes of it anyway. The second basic assumption is that we have a basic internal perceptual unit in our heads, and that basic unit is the JND. So according to this viewpoint, you can experience a difference of 1 JND from one stimulus to the next, but you can't experience half of a JND or 0.1 of a JND. So based on his work, Fechner came up with a law, and this is actually really the very first psychophysical law. Here it comes. Okay, it's a little bit more complex, but it's not too bad. Now, it's called psychophysical because on one side of the equal sign, we have S, which is amazingly a quantity for something that's in your head, your experience of a stimulus, the magnitude, how big it seems. Everything else on the other side of the equal sign is, well, basically physics. There's 1 over k, which is the Weber fraction. See how he's building on Weber's law. And then log to the base e of I, which is the intensity of the stimulus. Okay, that's a physical thing, definitely. So let's go back to that 2 light bulbs example. What happens if we do double the light intensity? And I'm going to oversimplify and set k equals to 1, and you can kind of play along if you have a calculator and plug in some values. Let's say that first light bulb has an intensity of 100. Run that through the formula S equals 4.61. Fascinating, but so what? Turn on the second light bulb, S. Well, S is different. The point is S hasn't doubled. Okay, so this says that, yeah, you can tell the difference when the second light bulb comes on, but it's not twice as bright. But what if you want to know what it takes to make something twice as bright? Oh man, you're going to have to work with the formula a little bit. It's not too bad. There's a simple way of describing that. Okay, let's go back to our first light bulb. It is above our absolute threshold. And I'm going to, again, oversimplify a little bit. I'm going to say that our light bulb is 10 JNDs above the absolute threshold. Okay, first of all, measure the absolute threshold, then find 1 JND above that, and then find the next JND above that. That one would be 2 JNDs above the threshold, and so on. Our first light is 10 JNDs above threshold. What you need to find is another light that is 20 JNDs above the threshold. This graph is a visual summary of Fechner's law. Once again, we've got the stimulus intensity along the x-axis, your internal sensory experience along the y, but look at the tick marks. The tick marks along the x-axis expand exponentially. So each mark is more than twice as far from the origin as the previous mark. But the ones on the y-axis are at regular intervals. Now, if we match up the tick marks, that creates this curve. Okay, go to the third tick mark over here, third tick mark, that defines that point. So this curve defines Fechner's law. It's a negatively accelerating function. each one of these tick marks represents certain units of JNDs. So it's a way of relating JNDs to particular stimulus intensities. Fechner is hailed as a genius. He's come up with this way of ascribing numbers to things that are going on inside of your head. That is crazy. And unfortunately, it takes about 100 years until people fully realize that there are some problems. Remember the problems with Weber's law? Yeah, Fechner inherited those problems. Oops. And if you would actually go through an experiment and collect data, it would not match the numbers that you got from Fechner's law. So Fechner's law, sorry, is also not a law. Oh dear. Now the good news is, it doesn't mean that trying to solve the scaling problem is futile. It just, people went about it the wrong way. It did take about 100 years, but there was a solution, and it was to do the opposite of what Fechner did. It's called direct scaling. It's super easy to understand, it's super obvious, and the reason why it wasn't used initially was because of this fundamental mistrust of the observers. We can't really trust people, and we certainly can't trust them to give us numbers. We can barely trust them to give us yes or no answers. With direct scaling, though, and specifically something called magnitude estimation, what we're going to do is ask people to give us numbers, basically. Okay, it's a little bit more involved than that. So first of all, you have to give people a reference stimulus. So you turn on a light that people can see, it's called a modulus, and you give it a nice round value like 10. 10 what? 10 whatever, it doesn't matter, just 10. Then you present them with other stimuli, and they compare these stimuli to the modulus. So if you show them something that they think is half as bright, they should rate it as a 5. If they perceive it as twice as bright, they should give it a 20, and so on. So pretty straightforward. So it's called direct estimation, direct scaling, because people directly give you a number. These results did not match Fechner's law, and instead, a power law described the results. I know you're expecting this to be super complex and really gnarly. It's not too bad. So all of this was discovered by S.S. Stevens. Here is Stevens' law. And it is elegant, I have to say. It really is. Because you might be thinking it's going to be incredibly complicated. No, it's actually not that bad. It is a psychophysical function, so we've got some different letters, so please be aware of that. P means the perceived magnitude. S is the stimulus intensity. K is a constant. It is not the Weber constant, okay? It's just a different constant altogether. What's really new here is N, the exponent, and everything really hinges on this N, which we'll see in a sec. So here's some graphs that all encapsulate Stevens' law. Once again, x-axis is stimulus intensity, y-axis is perceived magnitude. We're not changing that. And here we see 3 different kinds of experiences: electric shock, judging length or distance, and experiencing brightness. Now those lines are going off in very, very different directions. It does all hinge on the exponent. The good news is there's been a lot of work done, and you can look up the exponents in a book. In case you want to see some numbers, hey look, here's some numbers for loudness, brightness, smell of coffee, taste of salt, taste of sugar, and all kinds of different things. So it's really the exponent that defines the nature of the relationship. So there's 3 categories. If n is greater than 1, it's called response expansion. This is what the experience of electric shock is like. If you double the voltage, it doesn't double the pain or the sensation of shock, it more than doubles it. Your response is expanding. That's why it's called response expansion. Another possibility is a linear relation if n equals 1. I think it's pretty obvious there. Go back and take a look at the formula. So this is the case, the rare case of an isomorphic relationship, a 1-to-1 change. let me give you an example. For line length or distance here, let's take a look at some lines. Your modulus is the line on the left. I'm going to give it a value of 10. If that has a value of 10, what would you give to the line on the right? Would you say 5? Get your eyes checked. How about 10? Put your glasses on. 15? 20? 25? 30? 35? 50? 100? Okay, the answer actually is 25. 25. And if you didn't get it correct, maybe you should get your eyes checked. Okay, no, it's actually the way I did it. I gave you categories. If you just blurted out 25, that actually works better. The last possibility, n is less than 1, is response compression. For example, if you double the actual intensity of light, it doesn't double the brightness. Yeah, maybe it's a noticeable change, but it's less than a doubling. So, intensity of light, loudness of a sound, for example. Now, people realized that Fechner was wrong, but they were also reluctant to do away with Fechner's approach. There was a lot of resistance to that. So there were a number of criticisms that Stevens had to address. So one of the criticisms is, well, it's not, I mean, Fechner's law had this one curve, right? But for Stevens, there are these lines, and they're going off in all kinds of directions. They're crazy. We've got straight lines and positively accelerating and negatively accelerating, and people they just weren't accepting of it because the way the lines looked. Seriously, that was the criticism. Stevens, fortunately, knew what he was doing and took the same data and plotted a log-log graph. So you take a log of each axis, and then, oh, look at that. Now they're all straight lines. Isn't that neat? See, math can be our friend. And furthermore, you could calculate the slope of each one of these lines, and you know what? The slope is equal to n. Oh, that's beautiful. Math can be beautiful. But still, why these very different kinds of things? Why the 3 different categories of n's? Why? Why would experience of pain be different than judging distance, be different from experiencing brightness? Why? Why? Do you have an annoying kid brother or kid sister? Did they ever play the why game? They ask you why? Well, I'm going to school. Why? I have a class. Why? I need to pass this class to get credit for my degree. Why? So I can graduate and get a job and move out of home and get away from you. Why? Why can be an annoying question. And when it comes to psychology, people can ask the same question. Why? Fortunately, we have an answer, and the answer is because evolution. Because our senses evolved this way. Why do we get response expansion for pain? Yeah, we don't want to burn ourselves to death or electrocute ourselves, so it would make sense that we are exquisitely sensitive to things that cause actual or potential tissue damage. It would make sense that we are very accurate at judging distance. Like, how far is it to the edge of this cliff? I think you better be very accurate with that, okay? And it also makes sense to have response compression because it allows you to perceive in a large range of light intensities or sound intensities. So for light, you're not blinded in direct sunlight. You can also see a bit by the light of the full moon, for example. See, the answer is because. So everybody's happy and there are no more oh, look at, there's another criticism. So again, the fundamental mistrust of observers, people would say, well, you can't trust observers to give you numbers because people do all kinds of crazy things with numbers. Numbers could be all kinds of things. They could be nominal, ordinal, interval, ratio. What are they doing with numbers? So for example, let me ask you a dumb question. Which is the bigger difference, going from 1 to 2 or going from 2 to 3? Bigger difference. I know, you're thinking, they're the same. I can do basic math. Okay, but think of it this way. If you go from 1 to 2, you've just doubled, your number. But from 2 to 3, you haven't doubled. 3 isn't twice as big as 2, right? So maybe there's something to that. So how do you get people to do magnitude estimation without using numbers or giving us numbers verbally? Well, what if they responded by answering us using another sense modality? This is called cross-modality matching. Which other modality would you use if you're measuring vision or audition, for example? Okay, so what you do is you get a gadget called a hand dynamometer, and it can measure your hand grip strength. Now notice the person who's using this can't see the numbers, right? It's not pointed towards them, it's pointed outwards. And we show them a light. We tell them, okay, squeeze this thing a bit. All right, that's your modulus. Present them another light. Okay, if it's half as bright, squeeze it half as hard. If it's twice as bright, squeeze it twice as hard. So what they're doing is they're using kinesthesia, okay, muscle tension, to estimate quantity of other modalities like vision or audition. And you know what you get? What you get actually matches magnitude estimation. They work together perfectly well, so it's pretty much accepted these days. You don't have to use a hand dynamometer. You can just ask people for numbers. Makes things pretty easy. I'll stop there.